Good afternoon. In this rainy day, it's surprisingly cool outside. Doesn't feel like Texas weather. Um, we're used to it 100 degrees, not 75, 77, but we love it. And today's lab, we're going to cover AC circuits. Uh, and in this AC circuits, we'll put different elements like resistors, inductors, and capacitors in series connected to a AC source. Yeah. Uh, so AC source means the voltage supplied is alternating, hence the current is alternating. Okay. Last week we did the direct current or the direct voltage. Direct current, direct voltages are constant in time. They don't change over time. It's a straight line when you plot a time series. However, for alternating source, uh, the voltage provided by the AC source and the current are oscillating in time, as you see here. This is a time series graph, time in x-axis. As time moves to the right and you start at some values, here it's starting at the maximum values of voltage and current, which are called V naught and I naught, also called the peak voltage and peak current. And as they evolve in time, they oscillate back and forth like this, and hence these are alternating current and alternating voltage. Um, and they have their own frequency, a, and we can, instead of just I for current, since they are evolving in time and they are oscillating like this, so the current would depend on some constant peak value of current or constant I naught, and the angle, which is given by cosine omega t, and omega is the represents the angle change, the angular frequency in this case. And so hence, instead of current, for direct current, I is I, here I is I naught cosine omega t, meaning if if you were to plot this equation here, I equals to I naught cosine omega t, you'd get this blue line over here. Or in other words, the value of the current changes every second, every millisecond, nanosecond, depending on the frequency of the current. And here it is the maximum current, and as you move in time, the current decreases. At some point in time, the current is zero, and there is negative current. And here is the negative maximum goes to zero, and again maximum, hence that's why it's called the oscillating current. And now when you put for this lab, we will put three different elements: the resistor, inductors, and capacitor in series to alternating current, and we'll see how they all behave. And so the equation of the current, or the sinusoidal current, that has frequency f, means how frequency is oscillations per second, how many times they oscillate in 1 second, that's f. So the sinusoidal current, the equation is I equals to I naught. Again, I naught is the constant for this graph here, also known as the peak value. So the peak current, and for V naught, that's the peak voltage. And so the equation for both the current and voltage with respect to time are given by I equals to I naught cosine omega t, and V equals to V naught cosine omega t. And we can replace that omega by a linear frequency, where omega is equal to 2 pi f. So in this case, when you have a resistor in a AC source, the current and voltage is zero and maximum at the same time. So in this case, they are called to be in phase. So current through a resistor is in phase with the voltage. So as you can see here, they reach the minimum and maxima at the same time. And now when we put inductor in the circuit, inductor is a type of solenoid or a bent, wire, metal wire in this circular form. And this also acts like a resistance to the current. And why is that? Is if you have covered magnetism, that whenever alternating current flows through a wire, and when it reaches this circular portion of the inductor, and when current flows in a circular form, this is oscillating current. That oscillating current around a loop of wire produces oscillating magnetic field. And now in turn, that oscillating magnetic field, which is also the electromagnetic induction you will cover soon, that oscillating magnetic field in turn induces the oscillating EMF in the coil. That in turn induces current, which opposes the initial flow of the current. And now that induced EMF is going to oppose the initial EMF provided by the AC source, and we call that the back EMF. So hence, inductor in a circuit acts like a resistance, which we call the uh, inductance that we'll see in the next slide. So here it's a simple derivation. Here we take it from the theory part. Here your voltage across the inductor is the L is called the inductance of that inductor L, and inductance is measured in Henry H L di dt. And current, we assume throughout that current provided by the alternating source is I naught cosine omega t all the way, and replace that I, and we get V is equal to some constant here, omega times, it's again taking derivative, don't worry about it, it's not a calculus based course, d dt of current, which is I naught cosine omega. You take derivative, you get this function over here, and you put all the constant terms outside, omega, L, and I naught. These are constant terms, cosine omega t plus 90. So we get that, and we replace omega L I naught by V naught, where V naught is I naught omega L. V naught is again the peak value of the voltage, hence we get V equals to V naught cosine omega t plus 90. Compare that to current equation, I is I naught cosine omega t. You see that the voltage is leading the current by 90 degrees, and that's what we see it in the plot. They start at same point in time, however current starts much higher. That's 0 versus 90, and it's the current and the voltage, they both are out of phase by a quarter cycle. Right? There are 4 quarters in one complete circle. That's 0, 1/4, that's half, 3/4, and 360 degrees. And this in the resistance provided by the inductor in the circuit, the technical term is inductive reactance. And again, this inductive reactance is also the back EMF produced by the inductor as oscillating current flows through it. And so comparing this constant term here, V naught I naught omega L to V equals to IR, I naught R, again V naught and I naught are the peak values, that we see that V naught is I naught R, or we replace that constant V naught from the earlier two, we get R. This is the resistance of a resistor, but we are not looking, our inductor is not a resistor. It's just a material that produces back EMF, which opposes the flow of the current. So we call that inductive reactance as XL, which is equivalent to um, uh, uh, V naught over I from this equation, and this quantity here XL is called the inductive reactance, and XL from previous slide, that XL we can write as omega L, and omega we can replace by, again, that's angular frequency, that F is a linear frequency, omega, they have a relationship, omega equals 2 pi F, hence XL equals to 2 pi FL. And here XL and frequency have linear relation. You increase the frequency, so as you increase the frequency of the current, the inductive reactance increases. And for the graph, refer to the previous slide. And now the capacitive reactance. So we put resistor in a series with AC, resistor, inductor, and now the capacitor. So here we'll again derive a simple relation for V and I. So current through the capacitor is I naught cosine omega t, and to find the voltage across the capacitor here, we take this relation, capacitance relation, Q equals to CV, and where I, we can write I is rate of change of charge, dq dt, which is equal to I naught cosine omega t, and take the derivative, or I need to integrate this time here. The integration dq equals to I naught cosine omega t times dt. Once you integrate, I get q equals to I naught divided by omega sine omega t. So that's the charge on the capacitor. Now from here, V equals to Q divided by the capacitance. Replace Q by this term, I get V, voltage across the capacitor. V equals to all this term, or I can rewrite this as my constant, or the peak voltage V naught, where V naught is I naught divided by omega c. Hence V equals to V naught cosine omega t minus 90. So you see, for the inductor, it is plus 90. So here they're still out of phase by 90. So now comparing I naught cosine omega t to V naught cosine omega t. That is how the current and voltage varies in an inductor, in a capacitor connected in the AC circuits. These are the two equations, and from here you see that the current, which is the blue line here, the current is leading the voltage, which is red, by 90 degrees. Okay. Here, when you see, it seems like the voltage is leading, because in time the voltage seems to be ahead, but that's not the case. It's like here, if you see, at the peak value in time, if you compare time and the peak values, you see that the current has reached here earlier than the voltage. So that's the reason the current is leading the voltage by 90 degrees, or they're both out of phase by 90 degrees. And now the this there is something, this capacitive reactance, that changes the flow of the current in the circuit. We call that capacitive reactance as XC, and comparing that V naught is I naught XC to this equation, where V naught is I naught 1 over omega C. You put it all these two equations together, you get XC is equivalent to 1 over omega C. And again, omega C, omega is 2 pi F, hence XC. The capacitive reactance is 1 over 2 pi Fc. And so here, the capacitive reactance and frequency have inverse relation. That is, when frequency and the capacitance are smaller, when F decreases and C decreases, the capacitive reactance increases, that reduces the flow of the current in the um, circuit. And when Xc is larger, the current is smaller in the circuit again. And so we looked for resistor, inductor, and capacitors separately connected to a AC source, and you see how the voltage and current lags and leads in each of these elements. These are called elements. These are resistor, inductor, and capacitor. And we can add all these together in series to the AC source. The the change in potential around the loop is still equal to zero from Kirchhoff's law. There's potential change here, here, and here in each of the elements. So your V is positive, and these are all negative. V minus VR minus VL minus VC equals zero. Take it on the other side, we get this relation. Current through is still I equals to I naught cosine omega t, and the they're not in phase. The voltages across each of these elements are not in phase, so it's not simple algebraic sum. There is a lengthy derivation in the course book if you'd like to follow, but at the end you will get your V naught peak voltage that is related to all of these three elements as V naught, sorry, V square R naught, the peak voltage across the resistor is squared plus the difference of peak voltage on the inductor and the capacitor squared, which is equivalent to V naught is I naught R squared plus XL minus XC whole square. And we compare that V equals to I naught to V equals to IR, I naught times this, where R, that the equivalent of all the resistance of these three elements, the impedance, the resistance, the capacitive reactance, inductive reactance, and the resistance together, we call that the impedance. And from here, V naught equals to I naught, and replace that term by Z. We call that Z the impedance, which is defined in analogy to resistance and reactance of resistors, inductors, and capacitors. And so basically, the conclusion is that when you have these three different elements connected to the AC source, you know, each of them has individual resistance or reactance to the flow of the current, and we combine these effects together for all these three elements, and we call that the effective resistance, the impedance Z. And Z is equal to square root of R squared plus either XL minus XC square, or you can replace that by 1 over omega times C, which is 1 over 2 pi FC, or omega L, which is equal to 2 pi FL. And also for the phase angle calculation, in the previous slide we saw phase changes. We can use this relation here, the tangent phi. Phi is the phase angle. You can use either of these three relation here. If either you have voltage across inductors, voltage, if you have current and resistance, or if you have inductive reactance and capacitive reactance and resistance, you can use this. So phi would be tangent inverse of this term over here. Or you can also use cosine phi, and if you're cosine phi, use any of these uh, part here, depending on what you are given. Okay, now let's look at the simulation. So this is the lab manual for AC circuits. Completely stop information here. Some of you are still, missing to write your own name on the top. Here is the required theory that I just went over in the lecture, but this is for you as a reference. Based on the lecture, maybe your lecture notes, you should be able to complete these pre-labs. And so as a practice, for the lab, we do three different scenario. The first one is putting resistor and capacitor in a circuit, provide a AC source, and calculate frequency, voltage across resistor, capacitors, and so on. In second one, uh, we'll build a circuit with resistance and inductor in it, and finally we'll build one with all three elements, and check out how and calculate the current, voltage across its elements, and calculate the impedance, the theoretical and the experimental values. So to build, again, go to the link through the link to the PHeT simulation site, and here pick lab, and here you'll see all the required elements that you will need for today's lab. Uh, the first one was we're building RC, so put resistor and capacitor, and give some AC source, and give required values of resistance, capacitance, EMF, and measure all these things that it ask you in the question. So let me walk you through it. Need a AC source first. So get your AC source here, some wires. I can stretch it all the way. Yeah, I don't need a battery here. And that, and I need a resistor here. Put a resistor in that. What else I need? I need a capacitor, and okay. Here I can modify my values. The question is asking for 4 ohm resistor, 0.06 farad capacitance, and 12 volts. 12 volts of AC source at frequency of 1 hertz. Okay, and my capacitor is 0.06. What was the resistance? 4 ohm. And so my resistance value is 4 ohm. As you see all right. So you see how in the AC circuit, how the current and the voltage oscillate. So this is oscillating in time. We don't see the time, but if we were to measure that in time, you would see the sinusoidal curve moving out in time. And good thing I have an oscilloscope here. Let me bring my oscillator here, and so you see, so in time, how is my voltage oscillating back and forth depending on the frequency of the AC source. So here I can try it by increasing the frequency to 2 hertz. So now you see the frequency has doubled, and hence that the oscillation cycle has increased. But I want to do it at 1 hertz for now, and that's that. And so, the question asked, there are so many questions in the manual. I wanted to go one each, at a time. For example, there's one question where you have to measure the voltage across the resistor, right? That may be easy. Let me just bring the voltmeter here and put a um, voltmeter around resistor. Now that voltage is not constant in time, it's oscillating like this, right? Because that would be even here. So let me change my oscilloscope here. And oscilloscope gives the time series value of the voltage and current. And you see, as it is oscillate, this is my zero range. So once sometime it is at the peak value, which is 10 volts, which is giving me about 10 volts here. Is that my yeah, that changes. So my AC source is 12 volts, but the voltage changes across resistor. So the question is, what is the peak value of voltage across the resistor? So how do you measure it? So here, the key is now it's playing. It's the current is flowing through the circuit. My voltmeter here shows fluctuation between 10 and negative 10. But what is the peak value here? So the trick is you can stop it. And so when I was at that location here, my value of voltage was 4.09 volts, but it's not the maximum value. The maximum value is when that pointer here, gray dot, would be at the top. So try to stop that thing at the top. One more time. That's a little lower. That sounds, that looks like it's at the top, which is the peak voltage, and that's my maximum value of voltage. And when I stop it, it's giving me a 9.96 volts. Can I get any higher than that? That's 9.22. That's even lower. 8.59. 8.78. I don't know, I'm getting lower and lower. Okay, 9.33. That's the maximum I can get. And so the next, you can measure the voltage across the capacitor, set these values, and once you measure all those values, write down here, calculate your voltage across resistor, capacitors, and do these calculations and answer the question here. I think it's fairly easy lab-wise. However, the theory is important, and theory is, quite complicated. Uh, and that the next one is RL circuit, but we'll move on to RLC circuit, where we where we will add all of these three elements, resistor, inductor, and capacitor, which will pretty much look like this. I made this one earlier. Uh, give the required voltage, provide voltage across the AC source as it says, and here's your resistor, capacitor, and inductor of um, 10 Henry. Inductance is measured in Henry, Henry. That's 10H. 0.06 farad, and 4 ohm is your resistor. Here, one new thing, different thing is I've added a current meter, ammeter, right here in the circuit, so I can also have a current measurement across. I found a major current here and plate. If you have certain voltage here versus This is AC source provides certain voltage, right? Here it's not, you're not going to get the same voltage value across R. First of all, it is oscillating, and it's not what you provide here. There's a different voltage here, and what we're trying to do is we're trying to get the, so it's 12 volt we provided, and here the maximum peak value across the resistor I'm only getting about 9.33, and even in the graph, it's oscillating between 10 and minus 10, but uh, try to pause it like this and get the exact. Here I can pause it and get my maximum current as well, like this one here. I'm leaving this within the circuit about 0.26 ampere. Try it few times and see if you can minimize the error error values in current and voltage. And once you measure across all resistor, capacitor, and inductor and get your maximum current and voltages, the peak value of current and voltages, um, you can go through the questions 2 and 3 and fill the data table 6. Okay.